first of all, welcome, Dirk, for giving us a talk and sharing about your research. We much appreciate having you today with us. Let me quickly introduce the webinar. So today we'll talk about how to manage societies better than optimal. And very briefly about your background, Dirk, you are a professor of computational social science at ETH Zurich, and you are also a member of the external faculty of the Complexity Science Hub in Vienna. And you started as a physicist, and with your diploma thesis, you initiated the area of pedestrian, crowd, and evacuation modeling and simulation. And during your PhD and habilitation in physics, you helped to establish the fields of social, economic, and traffic physics, and you have won several prizes and also published in top journals such as Nature, Science, and PNAS. So this is impressive. With this, I would like to hand over the floor to you, and the talk is yours.
Hello over there. I'm very pleased to talk to you. I've been in Singapore quite a few times, and I'm also involved in a project together with Singapore and Christoph and many others. So today I will talk about how to manage societies better than optimal. You would think that's not possible, right? And I hope that I will be able to explain to you what this is all about within the next 45 minutes. We're now living in a time of big data, and in a minute, a lot of data is being produced, a lot more than we can ever imagine. But that has basically raised a number of streams, including Chris Anderson's stream, who said the end of theory would come, the data deluge would make the scientific method obsolete. And so basically people started thinking that if you just had enough data, then we could know it all. We would just have to look into the data and it would reveal the truth. So the question came up, can we now know everything? Can we understand the human body, brain, and personality, and many other things too? Can we now see what is wrong in society, in the world altogether? And can we fix the system where it's broken? For such and other reasons, one attempts to build digital twins, also digital twins of humans. And so basically, the idea came up that social engineers could actually fix the world with a control room approach. And basically companies and militaries and secret services around the world are basically building digital twins in order to come up with the best possible solution, you would think. And they're trying to predict the future. A lot of this is based on what the people in the field of AI have done, including Geoffrey Hinton, probably the most cited person in the world right now. And he's been working on the calibration of models, which is basis of digital twins. And then he dropped out himself from Google. So the godfather of AI, or the father of the AI god, as some would say, he left Google and warned of the dangers ahead. So what happened? What went wrong? So basically, the people trying to create digital twins of the entire world, including humans, were ignoring the complexity of the world. Already the game of life, even though it's based on 3 very simple rules, cannot be easily reconstructed with machine learning. And of course, there are a lot more complicated and complex problems in the world. So in a sense, digital twins are lacking complexity science, and this is really important to understand. And some of the reasons are that on the one hand, even though we have the best technology ever and more data than ever, data volume overtakes processing power. And so there's a lot of data that we'll never be able to look into. I call it dark data. And on the other hand, complexity, that's the red curve, as we go on networking the world, is even overtaking data volume. So that a very paradoxical situation occurs that as time goes on, we lose control. We lose top-down control, to be specific. And we need a new control approach, which is fortunately existent, and it's distributed control. I'd like to spend a few minutes on complex dynamical systems for those who don't know a lot about them. Complex dynamical systems are all around us. Our brain, our immune system, ecological systems, financial markets, society, our economy, turbulent fluids, traffic flows, large supply chains, social, political, economic, and ecological systems, group dynamics, all of that are complex dynamical systems. So we cannot just neglect them. They're all around us and they're making up life on planet Earth. Now, what is so special about complex dynamical systems? Well, first of all, there are actually limits of predictability. And we all know that because weather forecasts actually have a limited time horizon. And this is actually not because of a lack of data, but because of a physical phenomenon called turbulence, which implies that small variations could actually, over time, create a massive impact. There are other similar systems which you know from chaos theory, such as the Lorentz attractor. You can see over here, it's based on three very simple differential equations. These are non-linearly coupled differential equations, and that makes this complex dynamics. Now, importantly, even if we start with two initial conditions that are almost alike, there could be a difference actually in the 10th digit after the comma. Over time, the trajectories would separate, as you can see in the lower figure. And that establishes something that's called the butterfly effect. So even though it may be really difficult to imagine, the flapping of the wings of a butterfly could make a difference, perhaps even globally. And that is kind of shocking. It's difficult to imagine, but that's something that we need to take into consideration. Actually, there are some examples that you may know. Simple mechanical systems, such as this double pendulum, would think this is behaving in a very predictable way. However, let's have a look at what happens. Now, actually, this video shows you three double pendulums. So they're almost the same in the beginning. But as time goes on, those pendulums actually separate from each other. It starts to happen, and eventually they will behave in very different ways, as you can see already now. And as time goes on, it never repeats. And this is quite stunning, very unexpected for many people. And it has really very fundamental implications for our world. Also, in complex dynamical systems, there is a challenge of managing complexity. What you see over here are equations of the Lotka-Volterra system. This is a predator-prey system, an ecological system. And let's assume that there is a hunter that wants to establish a certain equilibrium that's considered to be healthy, represented by the red cross. As you can see, the circles that occur will never converge to that point. So the system behaves in a very different way from what people would expect. And that's even more true as many people interact with each other. Here we have a system of many cars. Drivers are supposed to drive smoothly. And what happens instead is actually a traffic jam. And this is based on a phenomenon called systemic instability, according to which small variations would actually amplify over time. And there would be a domino effect or a cascading effect that causes an outcome that nobody wanted to happen. Now, can we do something about it? Actually, yes. So what we do over here is we simulate the phenomenon you've seen before. A stop and go wave can be understood based on mathematical equations that are coupled with each other. And eventually, we want to understand what is the reason for this annoying stop and go traffic. So let's leave the car, let's take a helicopter to see what is really going on over here. And it turns out that actually there's an on-ramp where cars try to get on the freeway, and that produces very small perturbations. And those perturbations would be amplified and would cause the stop and go traffic. Now, let's assume that we introduce automated driving, autonomous cars. And those cars would drive in a slightly different way. We would keep the inflow to the road, however. So it's the same traffic volume that the freeway now has to handle. But you can see over here, the stop and go waves have disappeared. We have free traffic flow instead. So this is based on so-called mechanism design. There is no traffic control center that controls all the cars. Rather, we have changed the interactions. The cars measure distances and relative velocities, and they respond to this real-time data through a real-time feedback, and it allows them to stabilize the traffic flow. So we could say that with the Internet of Things, because this is all based on internet sensors, we can now make self-organization work 300 years after Adam Smith's invisible hand concept. Now, this is the time. And we need to realize that complex dynamical systems tend to self-organize. It means, in a sense, tend to do what they want. But establishing suitable interactions will produce desirable outcomes, and those outcomes will happen by themselves. So you somehow get it for free. And this is pretty amazing. And I will introduce to you now a problem where we have applied exactly that. Self-organized traffic flow at intersections. Now, what we want to have is what you can see over here, a system in which there are synchronized traffic flows where there are so-called green waves. What you don't know and what you don't see over here is how this is coming about. And in fact, it's based on local interactions at the intersections. There's no traffic control center that controls this. So how do we do this? Well, first of all, there's a short-term anticipation of vehicles. We measure the flow of vehicles that get into a road section. This allows us a short-term prediction. And we have basically used that information to define something like a traffic pressure. And as you can see over here, in the case of two pedestrian flows at a bottleneck, they're actually oscillatory flows. And it looks like there was a traffic light, but there is none. Instead, it's a pressure principle that creates this oscillatory flow. So what we've done is basically used a pressure principle to allow traffic flows to self-organize at the bottleneck, which is the intersection. And so we have compared 3 different kinds of traffic control. The left one is actually based on a traffic control center as we do it today in most cities. And in a sense, it works like a benevolent dictator that collects as much data as possible centrally and then tries to come up with the optimal solution and impose it on the traffic flow. The challenge, though, is that the optimization problem is NP hard. I mean, it cannot be solved in real time, even with a supercomputer. In the center, we have applied a simplified approach where we strictly optimize at each intersection for those cars that approach the intersection in the neighboring road sections. So every intersection strictly does the best thing possible, but it ignores what happens at other intersections. So we call this the homo economicus approach, a selfish optimization approach. And then on the right, we do the same thing, but when there's a long queue, we would first clear that queue before we go back to waiting time minimization. So intuitively, most people would think the centralized control would be the best because it coordinates traffic flows across many intersections. In the middle would be the second best, and the one on the right would be the worst. But in fact, it's just the other way around. And in the meantime, there are actually real world implementations. For example, in Lucerne, Switzerland, this is just half an hour from here. And they call it the super traffic light because it produces more green for everyone, something that's hard to imagine, but it just means that we are not wasting green time when it's not needed. Rather than imposing green waves, which is the thing you see on the top, this was the previous system, we adaptively use gaps as opportunities to allow cars to flow. And you can see that is reducing the red areas a lot. This is the waiting cars. So that means altogether, there's a lot less waiting over here based on the self-control, based on the local control principle using self-organization. Now, how much better is this? It turns out it's quite substantial. I would say surprisingly big, given that the system that they used before was, of course, a state-of-the-art system that they bought in the market. And the question is, what does that now mean for our society? Now, what I would like to argue today is we should build digital democracy. And digital democracy would base on collective intelligence. Collective intelligence, again, is about bringing the best ideas of many minds together. And there have been many books about the wisdom of crowds and collective intelligence. And those books work out that in many cases, the wisdom of crowds can be better than experts. But there are certain kind of preconditions for this to happen. Otherwise, it could be a madness of crowds, even. And one of the things that really matters a lot is the diversity of solution approaches. So diversity wins, not the best. And one of the nicest examples I've seen is the Netflix prize, where they wanted to have a better algorithm to predict the movies that people like. And it turned out to be a big challenge. And nobody could actually jump over the line that was required to earn the million that you could earn. And then eventually what they did was to combine the best solution with the second best and the third best. And surprisingly, that produced an even better solution. So how does collective intelligence work, or what does it require to work? There are different phases that this process needs to be organized in. There needs to be phase one, where there would be an independent exploration. So people would look for information, they would look for solutions, but the participants should not be influenced, not manipulated, and they should be different in their approach. In phase 2, there would be an information exchange between the people. So they would learn from each other. And in phase 3, they would integrate different solutions to come up with even better solutions based on a deliberation process. So what needs to change as compared to the situation today? Today, in many areas, we have a data-driven approach. This data-driven approach often uses not only big data, but also machine learning and AI. And the goal is basically to act like a benevolent dictator. That means that there's a social engineer or several social engineers that would use the data in order to try to figure out best possible solution and then impose it on the system. And so the question is this really the best thing we can do? A benevolent dictator would prefer things to be plannable, predictable, and controllable. Well, this is perhaps not too well compatible with democracy and freedom, but if it would work well, one could argue we should do that. Now, how might the benevolent dictator actually proceed? First, the benevolent dictator would collect data about the individual utility functions that might happen by means of mass surveillance. Then the benevolent dictator would determine an average utility function. Why that? Because optimization is requiring a goal function. And the goal function has to be a one-dimensional function. Otherwise, you cannot do greater or smaller than operations. But that is required to figure out which solution is better than another solution. So goal functions are one-dimensional. And to have this one-dimensional function, the benevolent dictator would average over the individual utility functions. Then for this, the best solution would be determined and then implemented. Now, here's the issue. An average utility function serves many people actually not so well, because we are not average people. Sometimes an average solution or the best solution for an average need would actually be quite bad for some people. We know that in society, goal functions should not be one-dimensional. Societies need multi-dimensional approaches. We want to improve in terms of prosperity, sustainability, resilience, health, education, culture, and many more things. So a one-dimensional goal function is oversimplifying societies and their needs. And then the question comes up, what are other ways to decide? Are there other ways? And the answer is yes, actually, we could vote. And what is so different about that? Well, when we vote, we don't have to agree on a goal function. People could have different goal functions, and we could vote, and still there's a result. Now, you could say we've done that in many areas of the world, and it did not work perfectly, and perhaps we need something better now. And in fact, it turns out that most of the time, majority voting has been applied. And it turns out that this is one of the worst voting methods. And there are various issues. One of those issues is that people are afraid of a tyranny of the majority. For sure, though, even if that doesn't happen, the majority rule undermines fairness, in particular spatial fairness. Why is that? So suppose you have a city with different quarters, and those quarters would come up with different projects to vote about. Now, what do you think happens? It turns out that in those quarters where most people live, of course, there will be most of the votes. And as a result of that, most of the money would go to these quarters. And typically, this are the central areas. So that means most of the money goes to the center while the periphery is being neglected. And in some countries, over a period of many decades, this has created quite bad outcomes, such as banlieues, that means social problems in the periphery. So it's clear that we need different, better voting rules. But what options do we have? So I'd like to remind how voting works to show what we can actually vary. First of all, what really matters is the voter preferences. And they need to be expressed. And that typically is done by means of a ballot. The ballot is the way to express the voting preferences, and that produces the voting input. That goes into a ballot box, which aggregates the votes. And as a result of vote aggregation, actually, there would be a democratic outcome. So we can actually vary two things. On the one hand, voting input, that means the way we express the preferences, and then second, vote aggregation, that means how we summarize the votes, how we come to the democratic outcome. Now, in order to do some experiments, we have created an app, which we call Vote App. It's a smartphone app that allows to experiment with different kinds of voting procedures. And we have done that in a laboratory experiment. And there are many different input methods. I just mentioned a few for illustration over here. Kind of the most common approach is approval voting, where there's a set of options and you would basically indicate approval of some of them. And so the ballots would go into the ballot box. Then there is a method called combined approval voting. And here you have more options. You can approve, represented by 1. You can abstain, represented by 0, or you can actually disapprove, represented by -1. Again, this goes into the ballot box. And then the third approach is called rank voting. And here, basically, people are asked to put the different options into the order of their preference. And this is then translated into a number of points. The best solution, the most preferred one would get 4 points, least preferred one would get 1 point over here. Again, that goes into the ballot box. And then there's cumulative voting. And here you have a certain number of points which you could actually distribute over different solutions. In this way, expressing how much you like a certain option. Again, that goes into the ballot box. Okay? Now, what happens in the ballot box? Well, in most cases, we do apply majority voting, as I said before. So basically, those options with most votes would actually be approved. Now, what we'll do now, we apply this to a setting where those different options have a certain price or a cost. So we have to invest, and there's a limited budget, unfortunately. And as it turns out, the majority voting actually does not pay attention at all to the costs, right? So then the question is, would there be other approaches that would consider the costs and thereby perhaps have some advantages? One way is applying the optimal knapsack approach, where you basically divide the number of votes by the costs, and then those projects with the best ratio of votes versus costs would actually be selected. And it turns out those would be different projects from what we had before, okay? Now there's another approach, and of course there are many more, but I'd like to leave it with that. There's the method of equal share, where every voter is imagined to have a certain budget to distribute over the different projects. And then those projects that accumulate enough money to realize them would be implemented, and the others not. I'm oversimplifying because there would be some project that accumulates some money, but not enough. And then money would be redistributed over other options, basically. What we care about is proportional fairness. Now, importantly, those different aggregation approaches would actually produce different democratic outcomes. As you can see on the left, the simple majority voting would often result in a situation where one project actually eats up most of the budget, and there's almost no money left for everyone else. Not so for the optimal knapsack approach and for the equal shares approach. And so this is interesting because it means that you could really make a difference by choosing different voting rules. Now, this was all quite theoretical, but in fact, we have done laboratory experiments. Not only this, we have also actually engaged in real-world participatory budgeting. Participatory budgeting has become quite popular around the world. One of the cities known for it is Barcelona. This is a jumbled title, sorry for that. It says, only this way digital democracy can be sustainable. And what we did is we did participatory budgeting, but we improved some of the rules. We did that in the city of Aarau in Switzerland. It's a small city. And they ran a project called Stadtidee. And so they informed the citizens about this participatory budgeting. And they were building on collective intelligence. I mean, they were inviting citizens actually to deliberate about what can be done to improve the city. And so there were all sorts of brainstorming sessions. We've been using the Mentimeter, among others. And you can see over here the map of Aarau. And people were using sticky notes to put their proposals of what can be improved in one place of the city to that map. That was the very initial approach. And so in the beginning, there were more than 100, actually 161 ideas proposed. And over time, some of them were taken out because they could not be implemented, and other proposals were merged. And so eventually, this was boiled down in a democratic deliberation process to 33 proposals. You can see 32 of them over here. And this is what people actually voted about. And what was really important also for the city was to create trust through transparency. So people were informed how things would work. They were informed about the voting procedures. We applied cumulative voting because in a laboratory experiment, it turned out that this was the method that people preferred and trusted most in. It will also inform that it's not just the number of votes that matters, but also the cost. And that had an interesting effect. That made many proposers careful to think about how much budget they really need. Because in other cities, it has happened that many proposers have gone for the maximum amount of money. And that made other participatory budgeting approaches pretty expensive and ineffective. Let's see what happened actually in Aarau. So points were distributed over different projects, and this is the outcome over here. So as you can see, the projects that were finally selected actually turned out to have a particularly good ratio between votes and costs. Voter satisfaction was particularly high for the approach that we used. And as compared to majority voting, which would have selected just 7 projects, the proportional fairness approach that we used actually selected 17 projects. And you can see that this actually also produced spatial fairness. While majority voting on the left would have given most of the money to central districts, the proportional fairness approach distributed money over all the districts. So all districts really had a chance to win through with one of their projects. Moreover, the approach was also more participatory and inclusive. So we had a better gender balance than usual. We had a better distribution over age groups. That means more younger and more older people were actually participating in this, and also foreigners actually. So in conclusion, democracy can be upgraded if we go away from trying to optimize a goal function, which is representing the average preferences of people, towards a system that allows different interest groups to get support for different projects that would serve their needs and interests. We would have, in the way that I've presented before, we would have more approved projects, more resourcefulness, more participation, more inclusion, more transparency, more trust, more satisfaction, and more fairness. So I think it's really justified to say this is better than just optimal. Democracy can be upgraded. And so I'd like to work out a little bit where else we could actually apply that. A couple of years back, I've proposed with collaborators to establish an approach that's called City Olympics or City Challenges or Climate City Cup. Now, the issue is that the world is faced with huge problems. And nation states and the United Nations have only made limited progress in terms of solving those problems so far. Same thing with global corporations. They've been trying hard, but our problems are still not solved. So I think we need additional complementary approaches. And the approach that we should add is do it yourself and do it together. And the City Olympics actually takes the idea of maker spaces and of hackathons and citizen science. It scales it up to entire cities and actually to networks of cities. So we suggest to empower civil society by digital means and to combine competition with cooperation. And for this reason, we have demonstrated on a small scale the Climate City Cup. The idea was to win together. And there were different disciplines, basically, where people were competing in order to come up with better solutions, like mobility-related disciplines, bike to work, for example, recycling, regenerative energy production, and many other disciplines could be thought of. So basically, cities would compete for the best solutions, and all the different stakeholders of cities, that means politics, businesses, the media, science, and citizens, most of all, they would all be participating in this. And so the approach would be localization rather than globalization. The approach is to think global, but to act local and diverse, to experiment, to learn from each other, and to help each other. And we have engaged in a little experiment where we have actually produced our own air quality sensors. We're still working on this project, and it's pretty fascinating because, just to give you an idea, the city of Zurich has 3 official air quality sensors, not more than that. We have 300 of those little green sensors. So you can really see how citizen science could make a difference. Right, so and the idea is that cities would compete, and then after that competition phase, the results that people came up with would be open source or Creative Commons. That means everyone could take them, everyone could improve them, everyone could combine solutions, develop them further. And this is how we could actually create collective intelligence fitting to local needs. So this approach would combine success principles of various systems, competition as we know it, for example, from capitalism, collective intelligence as we know it from democracy, experimentation, selection as we know it from evolution and culture, and intelligent design as we know it from artificial intelligence. And among others, this could be applied actually to make our economy more sustainable. Through participatory sustainability. So we all know that we currently have a pretty wasteful economy that uses a lot of fresh resources, produces lots of products that are then being pushed on people who should consume them, and in many cases they would throw them away after some time. And this is of course not very resourceful. Instead, we should reuse resources, we should recycle them, and this would really improve the sustainability of the world a lot. But very unfortunately, we haven't made so far much progress in terms of the circular economy that we wish to have. And I think regulation alone cannot do it. But there's a new approach, which would be based on the Internet of Things. That means billions of little sensors connected to the internet that could measure all sorts of things cheaply. The question is how we should use the Internet of Things. And I do think we should use it in a participatory way. So in principle, together, we would be able to map noise and CO2 and air quality and other externalities such as waste and all sorts of resources that could be reused and recycled. Positive and negative things could be really measured with the Internet of Things. And then the idea is that we would increase positive externalities by incentive systems, reduce negative ones, and ensure fair compensation. And for this, we have proposed something which is inspired by nature, because nature is a system that is already, in a sense, a circular economy. So nature has figured it out over millions of years of evolution. We should just learn from how nature does it. And interestingly enough, nature does not have a central supercomputer where all the data is being collected about everything that's going on throughout the world. Rather, circular economy of nature is based on local feedbacks, and actually many different kinds of local feedbacks. And so we have proposed to create new kinds of money, different kinds of money, which would be connected to the Internet of Things. So those measurements by the Internet of Things sensors would allow to define and create new kinds of money and new incentive systems in order to create new feedbacks. And those feedbacks would introduce forces in our economy that would lead to little improvements of everyone in response to everyone else. And so that would be a co-evolutionary process that would transform the economy towards a circular and sharing economy. Now, I said many different kinds of monies because a multidimensional approach is really a paradigm change. Today, a typical supply network looks like this. Now, if you look into how nature organizes supply networks, it looks like this. It's a metabolic network. That means the way our body solves supply issues. And you can see it looks very different. And there are a lot of cycles in there. Because cycles are not actually based on top-down control. You know, if you have a cycle, it's not clear, does A control B or B control A, or do they control each other? And in fact, it's most likely the last thing that happens. Like nobody is really in control. It's more like a coordination process that matters. It's a different approach. It's an approach based on symbiosis. So that's what we should learn. Yes, and we have actually now applied also voting procedures to traffic light control in a paper that was just published a few days ago, where we have suggested to apply voting at each intersection, assuming that every driver vehicle unit would have potentially different goal functions. So some would want to maximize speed or minimize travel time. Others would actually try to maximize sustainability or minimize stops. And so at each intersection, there would be a different distribution of goals. And it, accordingly, at each intersection, it would be decided in a different way, but based on a democratic voting process that can be automated to some extent. And so why are we doing that? Because classically, we've been trying to maximize one goal, be it efficiency or any other goal, it doesn't matter. And in many cases, we reached close to 100% efficiency for that goal. But when looking at other potential goals, those systems often performed quite poorly, as the blue triangle actually shows. Now, instead, according to our approach, the voting-based approach, we would get a solution that actually performs highly for different kinds of goals, I mean, in different dimensions. And I think this is a lot more favorable altogether. This is what we actually want. So I'd like to ask you to be a game changer. Now, the question is really how we can engineer a more responsible digital future. And for this, we need to learn to design for values. I did argue that democracy actually still has, also in the time of big data and AI, still has potential advantages because it can handle multiple goals. It can handle pluralism, it can handle diversity better, and diversity is known to be beneficial for resilience, for systemic innovation, and for many other things, for collective intelligence as well. And then the question is, what should be built into the digital platforms that we creating. And here are a couple of the values that I think should be paid attention to, values that matter. And I also think in a time where it becomes increasingly possible to manipulate people in what they're doing, if you want to stay in control of our life and what we do ourselves, then we really need to have informational self-determination, because otherwise it becomes possible that all sorts of companies and all sorts of states are interfering with what we're doing. And this is expected to create a big, big mess in the world. And I think we can see that already. So that's why I think we should be put into control of our data and our digital twins in order to make best possible use of data and information. All right. Thank you very much for your attention, and I'm very much looking forward to your questions.
Thank you, Dirk, for this inspiring talk. I would like to open the floor. We have a few minutes left before we close the hour. Is there anyone who has a question? Please, yes, Martin.
Thank you, Dirk, for this very insightful talk. I have a particular question about this example of the spatial distribution in ARA for the projects that you showed. I mean, it is true that with your approach, it is a more balanced spatial distribution, but still, as I recall, the big focus is on the center. And there are areas in ARA where there is nothing. So I was wondering, first of all, doesn't the outcome depend actually on the spatial distribution of all project proposals? So I would be kind of curious whether you have a map that shows the spatial distribution of all projects that were actually rejected, and whether that is kind of, you know, a balanced distribution too, or there were more projects rejected that are out of the center.
Mm-hmm. Yeah, it's a very good proposal, and I don't have that evaluation with me, but we could certainly look into this. Now, what I should say is it looks still a bit unbalanced, but many of the areas of the peripheral districts are large, and the population density is small over there. And therefore, it's a bit distorted in a sense. In the center of the city, there's often a lot higher population density because buildings are higher and so on. But what I recall is that in all districts, there was at least one project that won. And this is something very favorable, I would say. Something that couldn't be expected right away, and something that I would consider to be very promising. I'm not claiming here that we have already figured out the best of all possible ways of selecting inputs and aggregation methods, but I think we really have made a big progress in terms of understanding what are the things where we can improve democratic procedures. I didn't expect it actually to be so changing things so dramatically to the better.
Thanks.
Let's go to Nishant.
Yes. Thank you, Professor, for these insights, and particularly when you talked about these multiple objectives, and often they are not the ones that we optimize for. So in that regard, my question is about, in society, sometimes we have objectives that we are not aware of. So we might have, like you have three, you have resilience, efficiency, and something else, so three objectives. And then we can choose that, okay, this solution is good on all three, decently good on all three. But it's also possible that there are objectives which we are not aware of at the moment. So in such a scenario, would you suggest that we optimize for whatever we are trying to do and then stop somewhere short of the optimal solution, just to avoid that unknown objective?
I think really one of the advantages of the approach we have is it's not only capable of improving on several objectives, it's also capable of dealing with pluralism and diversity. So, we are living in complex societies which are based on a division of labor, among others, and so specialization. So everyone is, in a sense, different and therefore has different needs. But in many cases, we don't know well enough what the needs of different people are. And here with this approach, we give an opportunity for all groups of people actually to have a chance to improve things in their favor. So there could be improvements for all societal groups, and thereby not only there would be benefits for individual groups, but also for the interaction between those groups, because that is crucial for society to work well. And so those are the kind of secondary effects, which on the long term, however, play out as very important. And I think we cannot even estimate right now how much additional benefits those secondary effects would create.
Thank you.
Let's go to Felix.
Yeah, thanks also from my side for the talk. Very interesting, very diverse field of problems you are addressing. I have, in general, two questions. The first one is when it comes to distribution of information. This is something I would say implicitly in your approach, you assume that information is equally distributed. What if not, and how do you face that? And related to that, the second is some of your approaches are mapping to distributed optimization, and a lot of distributed optimization algorithms are not strategy proof. So that means if we are looking at the whole thing from a game theoretic perspective, we might find out that a lot of them are prone to manipulation, or that basically a malicious actor can basically steer things into one direction. Did you do some analysis on that, and do you have any measures to prevent that?
So malicious actors are, I think, a problem for all kinds of systems. Every system can be hacked, unfortunately. Whenever there is a mechanism, you can figure out how to use it for or against the system. So that's nothing particular over here. But yes, we need to pay attention to this, in particular, as there are malicious actors that are trying to interfere with democratic processes. Now, regarding the distribution of information, unfortunately, we have quite a power differential that results from unequal distribution of information. And I think governments should really seek to reduce that differential of inequality in terms of information, in terms of power resulting from that. Because in many cases, power, unfortunately, is not a solution to the problem that we have. Now, the third thing was kind of independent, selfish optimization of actors. This is not what I was actually trying to propose over here. That self-control of traffic flows actually work well for a system which pays attention to the neighboring intersections. So that means there's this not rules-less optimization that does not care about others. On the contrary, we have found that self-organizing systems work particularly well if the distributed entities would pay attention not only to their utilities, but also to the utility of the interaction partners, but not necessarily everyone. So there's a way basically to come up with solutions that serve individuals and the collectives well.
Thank you, Dirk, and thank you everyone for attending this webinar. I think we come to the end here. It's 5 o'clock in Singapore, 10 o'clock in Zurich. Is there any final burning question or any comment someone would like to share? Otherwise, I suggest we can close here, and I would like to thank you again, Dirk, for preparing for this talk and joining us and sharing about your research. It's very inspiring. I suggest everyone who was in the audience, if you want to know more about Dirk's work, please approach him directly, and I'm sure he will gladly respond to you. I wish with this good evening in Singapore and good day in Zurich. Bye-bye.
Thank you so much.
Bye-bye.
Bye-bye.